multi-frequency Raman generation, and it's actually a Russian, I'll get to that, that got me into this field. First, why even do multi-frequency Raman generation? It is a way to make, hopefully a way to make very short pulses. So I'm going to start the talk by even just trying to say, why do people want short pulses? Now yesterday I started my talk by saying, why was I the one student that got to do it, and I was the only student who was trying to squeeze the energy into a short pulse to make high intensity. And everybody else was just trying to make the pulses shorter to measure something faster. And so this is a big part of what we do in the short pulse business, is how to make pulses shorter so we can see something faster. And this has been going on, of course, long before the laser was invented, and so we're showing here Edward Meyerberg. And I don't know enough about horse racing, but apparently back 150 years ago, with the different types of horse racing, this was controversial. People said, yes, all the feet come off at once. Other people said, no way, at no time do all the feet come off. And of course, some people saw it, some people didn't. It was controversial, what are you going to do? And so Edward Meyerberg figured out that he could put a series of cameras along the way. He could time the shutters of each of these cameras to be opening up at the same speed that the horse would be going by, and he could take picture after picture, and he stopped the action by the speed of the shutter, which is a millisecond. Okay? Now luckily a horse is a large object, and so it can only move so fast. So the millisecond time scale stops the action of a horse. And you can see right here, this is the thing that stopped everybody. All hooves are off the ground, and so it put an end to whatever this controversy was. He proved it one way or the other. And so this is a long time ago. The speed is a millisecond, good for something massive like a horse. And what limited you to a millisecond is the fact that a shutter is actual mass moving. There is a limit to how fast mechanical motion can be. So now you skip ahead 50, 60 years, and we get to Harold Edgerton. He realized you can't open and shut the shutter fast enough. So let's put the object in a dark room, and let's have the light just flash on and off. And then the only picture you can see while the camera film is open for the whole time is only the light that comes from this short flash. And so now you're stopping the action on a microsecond. So he had come up with this electronic flash that would put a light burst out that lasted for a single microsecond. Here's one of his famous photos, which I've stolen from the web, and I see you're videotaping, so let's not get me into trouble, because I'm not sure I've got the right stuff here. But anyway, it's his photo, and I've stolen it from the web. And it's the bullet going through the apple. So now you can stop the action of a speeding bullet. Now this is still something with real mass traveling, and so what if you want to get something even faster? And here's the example I'm going to use, is what if you want to study the atomic motion of molecules? Now those of you who are quantum, and I understand many of you are going to be just cringing at my depiction of an atom as a ball. You're going to be cringing at my depiction of the bond being, you know, a line or spring. But one must stick with this little picture, because this is what we can imagine in our brains. Oh, I do, there we go. So the question now, obviously people, and again, if you're a spectroscopist, you're going to say, oh, we already know this from your spectroscopy, we don't need to short pulse lasers. Okay, but a simple example. Could we watch the motion of the oxygen compared to the carbon moving this way or this way? Okay? This motion is on the order of about 10 femtoseconds. So if we're going to stop this motion, the pulse has to be shorter than 10 femtoseconds. If you actually had a hydrogen that on any molecule, CH6 or whatever, and you want that hydrogen move, because it's the lightest atom, it's going to vibrate at 2 femtoseconds. So you're going to even want maybe smaller, less than 1 femtosecond pulse. But let's say this is what we're after, and it is what we're after. To measure this kind of motion, you need pulses that are on the order of 1 femtosecond. But of course, this is not like looking at a bullet or looking at a horse, where they use normal cameras. You can't even put your camera at the end of a microscope and see this, because this is sub-wavelength dimension. So we cannot just look at an image normally. We need a whole different way to image. And this is why we don't only need it short, we need it to have a lot of energy. And of course, this is all I do in life in science. I try to figure out how to make short pulse, intense laser pulses that nobody else has. Okay, that's my whole shtick. All right. So how are we going to see this molecule vibrate? Again, the atom is not a ball, so we're not even looking for a ball. We're just really looking for the center of mass motion. That's all we're asking. Can we do the stop action movie just like the horse? But now we're going to just watch the center of mass motion. We use something called Coulomb explosion imaging in order to say the two atoms are this far apart, the two atoms are this far apart, and that's it. And we'll take a series of them to make a stop action movie. So now here's how Coulomb explosion imaging works. I've now dropped this down even to a diatomic, because that's enough to understand Coulomb explosion imaging. So we have two atoms connected together, and we need to know how far apart are they. So we're going to go in with a short pulse, because again, this is vibrating at maybe 10 femtoseconds, and so the pulse has to be shorter than that if we're stopping the motion. And the point is what this short pulse has to do is ionize both atoms. So yesterday, I said that in order to do this, you could use the photoelectric effect, but this you're going to need a short pulse that's well into the ultraviolet, or in our case, we would use multiphoton ionization, which I talked about yesterday, which requires then a pretty high intensity. So we want a high intensity short pulse to make this happen. Once you've made it happen, you watch, and of course, I'm sure you've all in first year physics, or those of us who teach first year physics have fun putting the charges on the two pith balls, and we watch the two pith balls come apart. But of course, our two pith balls, and you can do it here easily. I'm telling you, in Canada, in September, so humid, never works. But anyway, here it probably works beautifully, and you see the charges come apart. These two charges, though, are angstrom to a nanometer apart. These are two charges that close together. There's no just coming apart. This is why it's called Coulomb explosion, okay? And so, depending on how far apart they were, you get the kinetic energy out, and you measure both the direction and the speed of the final fragments, and that tells you what the potential energy was, and the potential energy is 1 over r. So that gives you the r, and so this is how you do it. Okay, 2 more pictures I stole from the web. So here's some mythical, that's maybe too light to see. It's 4 atoms, and then there's this electron cloud. And then you're going to come in with 1 short pulse, okay, because this is not like a horse that's already running for you, but this would be like the driver of the horse, the jockey, that's what we call it, jockey of the horse hitting their legs or slamming the reins, making it go. So you come in with 1 and you make something happen. And apparently what happens in this mythical thing is that the electrons start to come just over here. So now, at a time later, and remember we'll do this time, later, but this pulse comes in, and this is the intense one, and it's going to ionize, and it sends this ion this way, this ion this way. These two stay as an ionic molecule, rotating and going off this way. The way we measure it is the molecules are skimmed through this, so it's a nice, you know exactly where they are. You come in with the laser perpendicular. These two plates have an electric field across. So if you start going this way, you will feel the electric field and come back. So it is the time it takes to get here, tells you how fast you were going, whether you're going backwards to start with or not, and then the xy tells you the xy blow apart. So this is how we measure then that final momentum, and so this is how we can determine exactly at this point in time between the 2 pulses what was happening and where these atoms are. So this is what we want to do, and really my colleague Joe Sanderson is in the next lab to me, and he's an expert in this. And I've been saying for 10 years, I'm going to get your short pulse laser to do this. He's still waiting. But anyway, I'm going to keep telling you my story. Okay. So I gave you this picture yesterday. If you want a short pulse, you need many colors. And in this particular picture, you will see that my color is, separation is evenly spread. And so I have a series of colors that with our mode locker has put together time right here, and I pointed out, in case you weren't there yesterday, that as you leave this point where all colors are peaking, that as you go away, many are peaking while the others are troughing, and that's how you cut the amplitude. The black is the addition of all the colors, and you make a short pulse, and it's approximately given by 1 over the bandwidth. It depends on the spectral shape. All right, so let's talk about ways to get these phased periodic frequencies. And I've already mentioned that we have laser mode lock. So here's a cavity, and this came up in a question after my talk that not everybody heard. But anyways, most people, when they hear the word laser, because it stands for light amplified by stimulated emitted radiation, we think the coherence of a laser comes from that stimulated emission. But that is not true. It's the starting point, but it is really the cavity that sets up the coherence of the laser itself. So one of the things that going from a laser to a laser is that we use these open cavities, and this open cavity only allows the frequencies that have a half a wavelength fitted in each time, and so the separation of them is C over 2L. Now then, when you learn about mode locking in textbooks, again, almost everything is from a theoretical point of view. And so the theory would show that you would add these Fourier series, and if you add this Fourier series, out comes this train of short pulses. As an experimentalist, that's not the way we see mode locking, because there's no way to say, oh, how do I lock all those frequencies together? There is no way. So we think about it in the time frame, and we say we must have a very fast shutter that opens up and closes, opens up and closes. And so when we make this short pulse, it must travel at the speed of light. And so every time this short pulse hits the output coupler, some 1 to 30%, depending on what kind of laser you have, comes on out. It then circles around again and comes back out. So this is a great, again, optical example of mathematical Fourier series. And so this is why I love optics. It just goes hand in hand with Fourier math, is that we see that we have to be a cavity that would be sustained in this cavity, you must have a frequency given by some integer number of the C over 2L. I already told you the Fourier transform is 1 over that. The pulses can only come out in time 2L over C. And so you can see the 1 over is coming from this physical process, that the frequencies must be separated by this, and the time must be separated by this. So this is great. You can make very short pulses this way, but note that all of the energy is trickling out once every round trip time. And so none of the pulses can be very energetic, because most of the energy stays in the cavity waiting to come around another time again. And so we require amplification, which is, of course, my main name of my game, in order to keep this going. Now, another question I get asked a lot is, did I know that the CPA was going to be as big as it was when we did it? When we did it, as I said yesterday, we did it with neodymium YAG going into neodymium glass. These are big laser systems, and they really only happened at these great big laser facilities. So if that's what we had been stuck with, it would not have been the great big thing it turned out to be. But this guy, Peter Moulton, was at MIT Lincoln Labs developing titanium-doped sapphire at the same time we were developing CPA. So, and it's also funny if you ever see the Sigmund laser book, which is my favorite laser textbook, I must say. I definitely have it on the shelf, and I have to look up something, written in 1984. He wrote that the first laser ever done was ruby, chromium-doped sapphire. And he writes in his book in 1984, the only sapphire that will ever laze. He was wrong, of course, because about the same time, Peter Moulton showed that titanium-doped sapphire was really, and still is, the leader if you want short pulses. It has a gain bandwidth, and don't ask me why, because I don't know enough about material spectroscopy, but it has almost 100 terahertz of bandwidth, okay? And 100 terahertz of bandwidth will give you down to almost 4 femtoseconds, and people can get 5 femtoseconds from tri-sapphire oscillators now. But if you want to amplify these very short pulses, then the center of your spectrum sees this gain, while the ones out here see half the gain, which means this gets twice the amount of power to this one and becomes, for a gain of 2, becomes 4 times higher than this guy. And so this is called gain narrowing, and you lose your spectrum. And if you want, gain of 1,000,000, you've really lost your spectrum. And so again, the big tri-sapphire CPA systems usually are running around 20 femtoseconds. They're not running around 4 femtoseconds. So we lose that chance of having a really short pulse if we want the intensity that we want in order to do our Coulomb explosion imaging. So now a different way, and the shortest pulses out there, and they're not looking at atomic motion, they're looking at electron motion, is attosecond, a pulse generation that comes from high order harmonic generation. I also told you yesterday that I quit working on high harmonic generation because I couldn't make the plasma. But also by the last year of my PhD, out came this French group seeing the 33rd harmonic. So why even try to see the 9th harmonic? They blew my PhD project right out the door. I didn't know how to do it. It was already blown out the door. So, there was many reasons not to do it. But this is slightly later work, but they had gotten up to almost the 100th harmonic. So they're now well into the VUV. If you want a short pulse, the central period has to be shorter, okay? So this is how they can get down to, it used to say 65. Now, I should never say what the record is because I don't keep, really abreast, but I now say just approximately 50 attoseconds. I think I'm still right about that. All right, so it's got this repeated spectrum. It doesn't look like it's equally spaced because, again, theorists will talk about frequency, but experimentalists only measure wavelength. All right, and this is why it looks like it's getting closer, but if you plotted it as frequency, these are equally distant apart. And the other ones are very close together. We can't even hardly see with the spectrometer how close those modes are together. And these ones are the color times 2 apart. Okay, so these are very far apart, but they make the shortest pulses. But the problem is you'll see that even though you're out in the UV, so we can focus tighter, the pulse is shorter, maybe this is a way, when I said at the very end of my talk, we're looking for that new Nobel Prize winning way to increase the intensity. We're going to have to get out into the VUV, right? So that our pulse can get shorter, we focus the beam down to wavelengths. Every order of magnitude shorter in wavelength or higher in frequency, we get 3 orders of magnitude in intensity. This is 2 orders of magnitude. So we should be up those 6 orders of magnitude that I say we need. The problem is the efficiency of the process is 10 to the minus 6. So you end up where you started, okay? So this is a great way to make really short pulses, but you're not going to do nonlinear optics per se with this, or the multiphoton ionization we need for Coulomb explosion imaging with this. And so that gets us to multi-frequency Raman generation. It's sort of like also being like Goldilocks. Mode locking doesn't quite get us short enough. Attoseconds gets us really short. I want to be somewhere, it's not too hot, it's not too cold, I want to be in the middle. So it's multi-frequency Raman generation. This is my favorite MRG spectra out there. It's from Masayuki Katsuragawa in Japan. And so I'm just going to show this beautiful, beautiful spectrum and how we got it. I'm going to explain Raman in a few minutes, but it really requires 2 colors. But it doesn't matter exactly what the 2 colors are. It matters what the difference in the 2 colors are. Those 2 colors must subtract, the 2 energies must subtract to get to the vibrational energy or the rotational energy that you're using, okay? But what they noted is that if they did use the specific 806 and then the corresponding 784 that would give you that right energy difference, that the 34th order would be exactly the second harmonic. And so they put in 3 colors. They put in these 2 colors to really drive that vibrational level hard so you can get strong sidebands from any other color you put in. But why not put in one that's exactly going to match up? And so you can see it was starting to fade away and then it came back up again. And so we have this enormous, enormous spectrum. You can certainly get less than sub-femtosecond, just less than sub-femto, not 50 attoseconds. But you can get short pulses with these spectra. This is a spectra taken from my own lab. Now, the other thing I'd like to point out, just in case any of you are imaging people or vision people, it is amazing how good the cones in our eye are. The camera people are trying very hard to mimic the 3 cones by their 3 filters that they have in color photography. And if you want to look at any of the colors in our clothes, of course they match very well. But if you're looking at absolute pure colors like this is, they do crumbing. Because this is a beautiful thing to see in my lab. We see these, well, we don't see these colors, these are the infrared pumps, but as soon as it turns red, we see it go from a deep crimson red all the way to a bright scarlet red, to an orange, to a yellow, to a limey green yellow, and each color looks different. And we can see 16 to 18 of these colors going across. Each one, our eye can tell the difference. But you can see that a camera just went, there's so many yellow, there's so many of this green, there's so many of that blue, and that's all it can tell. But anyway, it's beautiful. The other thing I want to point out, it's hard to see, but we're sending our light in this way, and it's infrared, but the camera starts to see it clearly. And then you'll see it gets whiter and whiter. And if you were there in my lab looking at it, it would actually look quite white by here. I think it's because the camera sees the infrared that we do not, that it still looks a little bit red to orange. But it would start red and become yellow. So right away it tells you that the multi-frequency Raman generation is not at all like high-order harmonic generation. High-order harmonic generation, that spectrum, theoretically you can just hit the atom, one atom, and see all of that. This is not true. We make it a little bit redder, but it keeps happening over and over and over. So we do know that as you propagate along, it is a cascading process. Okay, so let's now do what is it? Raman himself, did this back in 1928, so it does not require a laser. Raman, although I didn't allude to it yesterday, when Maria Goeppert-Mayer in 1930 was thinking about it, Raman's work had already come out. Now this is another tricky thing for those of us in optics. Raman, to us, is a linear process, because it's one photon in, getting you one photon out. It also goes linearly with the power in. The amount of light you get out goes linearly with the power that you put in. To molecular and atomic physicists, or even the condensed matter, if it's happening in a material like that, condensed matter, they would say it is a nonlinear two-photon process. And if you look, this process is one of the ones that she showed in her picture. Now, she showed it as a high one up and a little one down. So just scunch that all the way down here and have a high one and almost the same color back down, and this would be your vibrational rotational level. And so it's a nonlinear from the atomic or molecular point of view. So again, when I say nonlinear optics and multiphoton physics is the same thing, you have to remember that we subtract one from the multiphoton physics, okay? So to us, this is a linear effect, and we call it inelastic scattering. We go in with some color to some molecule, and we cause it to either vibrate or rotate. This means we have put energy in. If we put energy in, the energy must come from somewhere, and so it is inelastic scattering, and so you have to subtract that vibrational energy from it, and you get smaller Stokes, and same with the rotation. This would need to be smaller than that shift. All right, so now we're going on. Once the laser came along in 1960, this is different. This is nonlinear, it's stimulated, it's, there's various things it's talked about. So now you have a laser, which means you have, as I said yesterday, very intense light. This means that it goes linearly with this. We're making a lot of this red light. This red light is then naturally resonant with this process. So this is a two-photon resonant process, and it can't be anything but a resonant process because it's making the color it needs to be resonant. And so you are really driving this transition. Okay? So a lot of people will also call this molecular coherence. Unfortunately, we have many, many names in this field for studying much the same thing, but just from a different point of view. So you're really driving this, and so another way to look at it is you're putting a lot of population out of the ground and into this. Because you've now put your population into this level, well, your pump can then scatter from this level, because it's high population, and then you can scatter back to the ground, and this is how you see the anti-Stokes. And so you didn't see the anti-Stokes until the laser came along. So now this led to a big spectroscopic tool called CARS, Coherent Anti-Stokes Raman Spectroscopy. I guess it's easier to say CARS than CASORS. And so people were trying to then actually go in with two different colors and tune this color. Because you would be looking for what molecule is there, you would look for these various transitions, and you would tune through and see if you would finally see this anti-Stokes at that wavelength. And so again, in Japan, this group, it's not going to show beautifully, but anyway, this group was trying to tune their one color. And so their one laser, they started at the peak, but as they tuned through to the edge of their gain peak, they not only amplified this color, but of course the laser itself would rather laze at the peak wavelength. And so it had amplified spontaneous emission here and a different color here. It was not the two colors that they were doing the coherent anti-Stokes. They were just making these two other colors, and it just naturally went with vibration and rotation, and all of a sudden, they were not expecting this at all. They were expecting one anti-Stokes order as they tuned through, and they got 40. Okay? And they looked at this and went, wow, that's 1989, and they're going, isn't that cool? We see so many lines, and it got out to the UV. So that's beautiful. And so that started this whole thing called various things, but I call it multi-frequency Raman generation. And there it is. So what is it? It is a cascaded process. It really is just a third-order nonlinear process. It's not like higher-order harmonic generation, which is a high-intensity effect. It is a third-order nonlinear optical effect over and over and over again. Because now we're not just having one, low power. Usually when they did CARS, one was strong and one was weak. Now we're going to put in two strong ones, and we are really going to couple this dipole. And so we're going to have 50%, ideally it would be 50% population in both levels. So now you're actually making a lot of anti-Stokes. All right, and once we make a lot of antistokes, but we still have 50% of the population up here, you can scatter and scatter and scatter, and this is as you go, you make more and more and more of these high order terms. You also can go down, down, down with Stokes, but if you're trying to make short pulses out of it, who cares? We have to get to the shorter wavelength. So we're not going to worry about going down, we're worried about going up. So one of the groups, Stephen Harris's group at Stanford, and Sokolov was his grad student at the time, he's now at Texas A&M, they did this, and they just took 5 of the orders, and they timed up 5 of the orders, and they showed that indeed they could get pulses. I think at this point it was 1.5 femtoseconds, and I think using multi-frequency Raman generation, the least has been 0.85 femtoseconds. So they've shown that indeed we can get single femtosecond pulses using this process. But these guys are using 10 nanosecond long pulses. And so they're very narrow spectrum. So I'm going to go back and talk about the difference, again, between a mode-locked laser and higher harmonic generation. So just to see what the difference is here. So mode-locked laser, so again, these are transform-limited objects, okay? And so we have to keep in our mind what do we mean when we Fourier transform from the frequency space to the time space. It always means the smallest thing here is the biggest thing here. The biggest thing here is the smallest thing there. So again, the biggest thing here is the whole gain bandwidth of the laser, the bandwidth that you can make your laser operate at. Okay, so Thai Sapphire would have it even shorter than this 10 terahertz, but I've taken 10 terahertz as a nice good number for a short pulse laser. And the 10 terahertz Gaussian goes as the 0.4 over the 10 terahertz, and that would get...
Can we stop the movement? So sorry.
It's okay. This would give you a 40 femtosecond pulse. Okay? And so if you have a 40 femtosecond pulse, that's as short of a pulse you can have. Again, I've already said the separation of these modes gives you the separation in time. So it was, 10 nanoseconds is the round trip time of most lasers here. But then, I'm pointing these out is how thick are the modes. If you really had a perfect cavity mode, you would have to have 100% mirrors. You could have no losses. You could have no dust kicking anything out. And so this is not possible. And so in lasers, we only have what's known as a quasi-mode. It is this that gives us the coherence. It's not the bandwidth of the laser. It is the bandwidth of these modes that gives us the coherence of the laser. Okay? And so it may be microseconds to milliseconds. It depends on, how big your output coupler probably is. And so that really just tells you that these pulses are going on and on and on, exactly phased perfectly for a microsecond to a millisecond. And on this 10 nanosecond, we have many, 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 many pulses. The energy is coming out in these many, 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 many pulses, so I've already said we don't have much energy per pulse. Now, on the other hand, if you want to amplify this, and if you're going to amplify these pulses, what you're going to do is reduce the rep rate, because the energy is the energy. So in 1 second, so much energy comes out of a Thai Sapphire. If you then drop the rep rate from 100 megahertz to 1 hertz, you can pick up that kind of energy. You can pick up those 8 orders of magnitude in energy if you want. Okay, and that's how the great big laser I showed you fired once a day. Okay, now it wasn't because it was held to that. That was a thermal problem of how to get out the thermal energy. But in any case, if you Fourier transform that, and you pull these things apart to be, microseconds, milliseconds longer, that tells you these modes have to get closer and closer, or actually they don't. They get wider and wider, and you fill it in. It's a weird thing. It can make your brain go crazy if you think about it, because you go, I'm just putting in maybe a Pockle cell switch and saying I only want 1 pulse. It automatically is saying then we're filling in all of this spectrum, because it has to be a continuous spectrum if you're going to only have a single pulse. All right? Because if you have a single pulse, this is going to infinity, and so the separation of the modes must go to 0. Keep that in mind. Okay, so now then you have this amplified pulse. It's this continuous spectrum of 10 terahertz. This is what makes the harmonics. You get every other harmonic, because again, it's isotropic homogeneous, so you can't have the even nonlinear orders. You only get the odd. So it's 600 if it's a 300 terahertz center frequency, 600 terahertz between them. That means that in time, these very fast attosecond pulses are coming at you 1.7 femtoseconds apart. Okay? So then you look, and remember the biggest thing here is the smallest thing here. So this 10 terahertz, 40 femtoseconds. So these 40 femtosecond pulses give you a 40 femtosecond train of pulses. And so if you really want your energy just in one, you want to stretch this as much as you come or bring this one down as much as you do. This is why the attosecond crowd use 5 femtosecond pumps, okay? And then they can maybe just have one pulse in their attosecond pulse. Okay, so this is the difference. So now I'm going to talk about the different types of temporal regimes of Raman generation. Where I showed you that they already just took 5 orders and timed them up, they're in the adiabatic regime, long pulse. That means their spectrum is narrower than the coherence spectrum of the rotation or vibrational level you're talking about. On the other hand, you could use these amplified 20 femtosecond pulses. There would be so much bandwidth in there, the 2 colors you want are inside the one, and it would just be the same short pulse, but you would pull the blue out going up and you pull the red out coming down. The problem is then, you actually go right across this whole thing and you don't get a discrete spectrum. And you may wonder, well, why do I want a discrete spectrum? Because some people use continuum generation to make short pulses as well. I'll come back to that. And then this transient regime, that's where you're in between. So this is nanoseconds, this is femtoseconds, this is sort of picoseconds. Okay? This is where the time duration of the pulses is sort of matching the coherence time. I've got it a bit bigger, but you know, this one doesn't look like it's much smaller, but it would be much, much smaller. This one's the same order of magnitude. All right, so now we're going back and we're going to look at these two. It's the same idea as a mode lock laser versus your attosecond in a way. In the adiabatic MRG, you have these very narrow lines, which means that you have 100 femtoseconds between the pulses, 1 femtosecond pulses, and that's all good, but remember it goes on for a long, long time, and so your energy per pulse is not there. So right now, the only groups that have managed to compress these pulses have worked in the adiabatic regime. So we've had single femtosecond pulses, but always much more like a mode lock laser. They're coming out long, long trains. Ideally, we would like to be doing it in the transient MRG, where we now have some thicknesses because we're going in with shorter pulses. And so we would have maybe just 400 femtoseconds, our single femtosecond pulses still separated by 100. And obviously we would even like to get this maybe down to 200 femtoseconds. So these guys are down quite a bit, and all the energy would be in the single femtosecond pulse. So this has been our goal. We've been aiming for this. I've been telling my friend Joe he's going to get this. And now the rest of my talk is going to be about why he hasn't gotten it. Okay? So, oh, let me get to my Russian friend here, Oza. Well, not so much because he didn't like me the last time he came. But anyway, so I haven't seen him since. But anyway, the laser did not work so well the second time he came. But you know, it's what we can do. So he saw the laser that I had, which I'll explain in a minute, 2-color laser we had gotten to work. And he was in Russia, and at the time, the Russians were having trouble having a lot of money for experimental work. So he had this way of doing multi-frequency Raman generation, and his theory showed that the efficiency was higher in this transient regime. Now he had this whole mathematical way of looking at it, but let me give you my take on it. In the adiabatic regime, even though I couldn't draw it this way, the bandwidth of the lasers was much smaller than the coherence time. And so you're wasting all of that other energy that's there. The transient regime, you're really matching your whole bandwidth of your laser with the whole bandwidth of the transition, and I think that's why you get a much more efficient process. His research also showed that if you could control the group velocity dispersion and make it 0, that not only did you get a much broader spectrum, but it actually favored the anti-stokers. And so if you're trying to make short pulses, this is what you want to do. You want to be in the transient regime, and you want to have 0 dispersion if at all possible. So he came over, and we decided, can we see this or not? This is why he came. This was the first laser that I built at Waterloo. Now you may ask, why did I bother building such a laser? This is a Ti-sapphire laser that instead of trying to make the pulses as short as possible, instead of trying to make 5 femto or 10 femto, we actually pull the bandwidth apart with some prisms and slice out just 2 pieces of it, so we can have synchronized short pulses, but there may be 100 femtosecond pulses rather than 1 10 femtosecond pulse. Why am I doing this at all? Because my husband followed me to Canada. I had followed him to New Jersey previously. He now followed me to Canada and had to take an industry job. He had been at Bell Labs, and he got to take his equipment with him. He had developed this two-color oscillator. So I inherited this two-color oscillator and thought, when I became a new assistant professor, what would I do with a two-color oscillator? I'd CPA it. What else would I do with it? So here we go. So it's a standard oscillator stretcher, amplifier, compressor, only we take the two colors that come out. We can't afford a grating that you would just have one beam with the two colors, because gratings get very expensive if they get big. So luckily our two colors come out of two different mirrors, and so we could put them at different angles, and we had to change this depending on what colors we wanted to work at, so that they would each go at their own angle to come off together. You go through the system and come off, collect it. We then would put them together, we'd amplify it. This is a standard amplifier that most CPAs would start with. All we did was in one of the arms put prisms again with slits to say these are the only two colors to amplify. Okay? Because again, just like that Japanese experiment, when they started to move away from the gain peak, the laser itself goes, no, you may want me to laze here, but I'm going to laze where I want to laze. Okay? So we made sure you don't get to. Okay? So you're going to laze where we tell you to laze, and then we go off the grades. Our grades are not perfect because if you watch, we come in at two different angles and go off of one, and more for laziness than anything else, we go in with one and come off with two. So they cannot both be matched sets of grades. Here just shows that the idea worked. The top traces is the oscillator. You'll see when we really pulled them apart, there was gain pulling at the bottom because the gain is going to change very quickly on this side. It's very flat on this side. This, I think, is that we just ran off the gratings. You know, I think we would have had a smoother trail there, but it seems to work. So that's fine. So this is what Leonard Losef saw and wanted to use this laser. And so he suggested SF6 as our Raman medium. So sulfur hexafluoride. He came, the first time he came, we did in something else. He came back the second time. Sulfur hexafluoride. We have these 6 fluorides, and the Raman vibration we're going to use is the symmetrical one where all 6 Fs go in and out, in and out, in and out. It's a breathing mode. If you use this one, you don't have to worry about rotations. There's no rotations because of the symmetry. So it's a nice clean one. There's no other Raman levels near it, so we can just really distinctly see MRG from this one level. We put it in a hollow fiber. We started with 1 meter. I think most of our work now is with a ½ meter. We can change the pressure down to 1 atmosphere and up to 3 atmospheres. And so this is something I just got off of, PowerPoint. And so this is not our best spectrum, but it's sort of matched up. All right, so this is the experiment. So I had a master's student, Fraser Turner, working with us this time. And so the first thing to do is just turn up the energy because it's a nonlinear process. It should go better and better with energy. And sure enough, better and better. And you'll see it also doesn't do much on the Stokes side, but we got more and more anti-Stokes. This is what we want. We want to get out into the blue so we can get single femtosecond pulses. This was looking good. So that was 2 to 4, it's just twice the energy. We could go to 6 back then. Going from 4 to 6, you'll see we got stopped. We got stopped, and also we saw this sort of continuum showing up. And so we started to ask ourselves, were we competing with self-phase modulation? So again, if you came to my talk yesterday, this is the thing I demonstrated with the slinky about how if you have a short pulse, you can make these extra colors. So we were thinking we were going in with a pulse that, and we didn't know which was the cart and which was the horse. Is it because we started making self-phase modulation that we stopped making MRG, right? Or is it something that stops MRG and so there's nothing left but for self-phase modulation? This is what we were thinking. So the first thing to think, and then of course you go and read all the literature and see if anybody else is seeing these things, and everybody said don't use short pulses, use chirped pulses, which again, is something we can do. So, so now, I actually went on holidays, and I left Fraser. I said, okay, so you've done the energy range. The other thing you have to do is look at what the phase matching is doing, because Leonard Losef has already shown us that we want to have zero dispersion to get the most orders. And so Fraser was by himself working, and he said to himself, well, okay, I can do the whole experiment, but let's just do something quick and dirty first. I'm going to cut the energy in half and see what that spectrum looks like, and then I'll go back to full energy and cut the pressure in half. Because from the nonlinearity point of view, both should give us the same result. If dispersion isn't doing anything, then we should get the same result out. And as you can clearly see, that when we dropped the intensity, something changed, we had less. But when we halved the pressure, we didn't really get less, but we got this huge continuum. So let me tell you a few things changed between those two experiments. One was the original experiment used a 250 micron hollow fiber. Hollow fibers work not like regular fibers, hollow fibers work on grazing incidence. The same thing if you skip stones on a lake, okay? So it skims on down the side, and if you have a big fiber like that, there's hardly any dispersion notice from that, and you just have the dispersion of the gas. But if you go down to a smaller diameter, this leads to more and more scattering, and so you see the negative dispersion of going in and out of the glass like this. And so you could go through a dispersion null when we drop down to atmospheric pressures by using the 129 micron. And also now we're going to use chirped pulses. So the first thing to note is that you see this continuum now here, but not where the two pulses are really intense. And so it really can't be self-phase modulation. We're still puzzling what it is. It can't be self-phase modulation. All right, also, when you cut the pressure, for some reason, it goes bluer. The other thing to note is that my master student left this adorable message on my phone. I kept 3 messages from my old phone thing. Now it died completely, so I don't. Each of my children calling home for something, just so I'd have their voice. And my one grad student said, "Donna, you should be here. It's glowing green. It's not glowing white. It's glowing green. You're missing it." And it was true. I was missing it. Okay? So he was adorable. Anyway, Fraser Turner. So you can see that the green is actually the same order of magnitude as the pumps. That was one thing to notice. It almost looks like there's this total continuum, but on the blue side of the peak, it's dipping into the continuum. And on this side is what we now still call the red shifted shoulder. And since then, we have been trying to figure out what is the red shifted shoulder. And we do think the red shifted shoulder is what's causing this whole continuum. So, of course, he did do the experiment I told him to do while I went on vacation. And he did change the pressure, and then he also plotted where the dispersion null would be. And so the main thing to notice is that where you see continuum has nothing to do with where the dispersion null was. And what we thought it might be, since it's not really from the most intense pump, it could be that where the dispersion null is, those colors are traveling together and making a shorter pulse, and that shorter pulse would cause the self-phase modulation. But it doesn't line up, so we don't think it's that. Okay. So then we looked at other people's results. And this comes out of John Marengis's group at Imperial. And they looked at both hydrogen and methane, so it's not SF6, 2 different gases than what we're using. The black is for if they just put in 1 pulse and the other for 2, to show you that you only get MRG if you have 2 strong pump pulses. So you only get these, right, if you put in both. And then they changed the chirp. So this is one of the places we look to see, okay, we should chirp our pulses. If you go with short pulse, you only get continuum. The more you chirp it, the longer the pulse, the more individual orders you get. But note that they see these red shifted shoulders. Some of them are quite big. They also seem to see these dips in the otherwise continuum on the blue side. So they sort of agreed with us. I've talked to John Marengis a few times. I said, "Did you think about what this means?" He said, "No." And the reason is that, of course, everybody working in this field, we're just trying to get the most orders. Because if you get the most orders, you get the shortest pulses. But Fraser and I looked at that and just went, what the heck is going on? Now, this works for me because I knew I'd done CPA, and so I didn't have to try to do something great anymore. But now I realize I wasn't fair to my students, okay? Because I thought, well, that's just a fun thing to study. Nobody else cares, and so we don't get huge citations. But to me, it's a fun thing to study. Now I'm thinking, maybe I should help my students more. But anyway, you never know. If we really get something big out of it, it could be good in the end, but until then, we don't know. Okay, so we might have to wait 35 years and I won't be here to see it. All right. So then, I was actually sitting at another conference with somebody else, not me or Shan or Alex, gave this talk and showed this picture. So I was sitting with me or Shan so I could ask her the question. Now, so these guys have the very short pulses, so they could do impulsive Raman, but they don't. They take the pulse, they divide it in 2, and then they time delay it. And then by time delaying these two pulses, you take the instantaneous frequency separation and you can tune through a resonance. Okay? This is now, the resonance is this instantaneous separation between the blue here, same pulse but separated in time, and the red. And so they were tuning through to do this, but let's not worry about that. Okay? So, but also, this is not off a gradient. These are solid, so now we're not even talking about gas targets, we're talking about solid crystals. They have their two pumps going in at two angles, and the phase matching is now done by what angle the Raman order goes out at. And so the Raman orders are these little dots all the way down, okay? But then I said to Mioshan, what are those big blobs of energy? You've got more energy in your big blobs than you have in your Raman. And he goes, well, we don't really know. We think it's forward mixing. I went, nah, we've already checked. It's not forward mixing. So let's show you that. So again, we had two pulses. We already had to chirp them anyway to make them long, so we didn't see the continuum on the pump pulses. So ours are set. We have our two-color laser that we set them to be 23.25 terahertz, which is the Raman transition in SF6. But we can then tune away either to the blue side or the red side by changing this. You'll notice that I do time backwards. My students will not show the pictures this way. Again, as I said, I'm a Rochester student. We learned that light only goes left to right. So when I see pulses, the right-hand side has to be the front of the pulse. I'm sorry, to me, I don't understand it if it's not the front of the pulse. So this is the beginning of the pulse, so time has to go that way. All right, so these are positively chirped pulses. They just look negative because of the way we time. All right. Of course, we can, that's if your gratings in your CPA system are too close together. You can make the gratings too far apart, and you have the opposite chirp. And so you should see the same thing, walk through the same resonance, but it would just be in opposite time, right? So one would make, if the lower one goes forward, it does one thing, it does the opposite if it goes backwards. And now let's see it. These were a bunch of undergrads, one after another, I had each term, trying to help me get this done. So here's zero detuned, positive, negatively chirped pulses. These two are then the same time delay, but one goes blue and one goes red, and these are the same time delay. So these are both blue detuned and both red detuned. What we noticed, and this is the only time we've done this experiment, so we haven't gone back to even think about it, but what's weird is that it never left the Raman level. It just went exactly where it was supposed to go from the Raman. We don't know if maybe our chirps weren't as perfect as they were. We did not have any frequency result optical gating yet. We just had an autocorrelator and a spectrometer. If you look on these ones, you never go to the blue side. Even when you're zero detuned, you'll see the red shifted shoulder is there and the Raman is gone. You still have the Raman, a bit of a red shifted shoulder even when you're blue detuned. And when you're red detuned, you're really well away from where the Raman is, and you really only have the red shifted shoulder. And the red shifted shoulder doesn't seem to come from this level. It's like it's this red shifted shoulder, and then if you took the frequency separation there and multiplied it by, 16 or whatever this is, you would come to here, okay? So that got us thinking. Well, this shows that if it was four-wave mixing, it would go like this, and it didn't go like that. And so we went, it clamps at both ends. It never really goes blue. It always stays red. And so we went, what is going on? What is going on? So then we looked at this paper. Again, now this is Harris's group, Sokolov, this is obviously his PhD work, MRG. And they have the 8 to 10 nanosecond pulses. They're going to change the detuning. And what they saw was that one of these two lines, this one here, will be where they're on resonance. When they blue detune, they don't see much difference. But when they red detune, they get many, many, many more orders. So they thought, well, this is because of two photon Stark shifting the levels, and you actually have to redshift to stay resonant with the two photon Stark shift. So now this is where we're going to get really into quantum optics here, and so you're going to have to, and trust me, in a few slides you'll be beyond me too. Okay, so this is the theory. Don't worry too much about it because obviously it's complicated. But the one thing I'll point out, and I've just now started to get a theorist to help me, because the problem is, the only theory there, stay here, is the fact that you start with this fact that your electric field in time is going to have all of these orders. And to start with, at early time, is you would only have the pump J, call it 0, and the -1, call it the Stokes. All the rest of the A's would be 0 at the beginning of time. And you're going to watch all of these A's grow as it propagates along, and you see whiter and whiter spectrum. But this then says it can't possibly help you find the redshifted shoulders because they're nowhere to start with. You can only grow the orders you have. There's nothing to say these other shoulders should exist. So we're missing part of the picture here. And I'm no theorist. So luckily I've got a group in Toronto starting to work with me. All right. And then of course this is the dipole you're driving, and it's a nonlinear interaction between the fields and the dipole. And so that's how the dipole changes with time. Here's how the population changes with time. And here's how the fields change with time. And again, it's the dipole and then either the Stokes or the anti-Stokes. Either you're dropping down or going up. So that's all great. But this is, so when they said it was the Stark shift, what they talk about is this term right here. You will see that this is the Raman. This is one pump and a different pump. But if you're strong enough to see a third-order nonlinear process, then of course what you're always resonant with is your one photon up and that same photon down to the same level. That one's always there. So when you do just the single photon one, and I'm going to explain the single photon Stark shift, you don't have a difference between these two because this one doesn't exist, right? You only have the one. And so we sometimes call it the Stark shift. We sometimes call it the Rabi frequency. They're the same thing. In the two photon crowd, they seem to separate it, and they call this one Stark, and they call this one Rabi. Why not? It's two different things. We'll call them two different things. So let's look at it. So I kept thinking, okay, I have to try to understand this. I even teach the nonlinear optics course to the grad students. I teach it out of Boyd's book. Let me go back and see if I can understand what the heck is going on with the Stark shift that would cause these redshifted shoulders. All right. And so first let me explain, what is the one photon Stark shift. The one photon Stark shift is, say you have two atomic levels, A and B, and you go in near resonant. And obviously much nearer to resonance than what this picture is showing, right? But if you're nearly resonant, then this is when you can get the Stark shift. When you're nearly resonant, you cannot use this Taylor expansion expression in nonlinear optics I talked about before, because there's always this denominator function. And this denominator function of this omega AB minus your omega would be going to 0, which means you've got this infinity. So there goes the fact that you cannot have Taylor expansions where your terms are going to infinity. And so this is why they needed a whole new expression and a whole new physics to explain these things. And so what they came up with was that instead of having photon states and atomic states, you actually have coupled states. Okay? And so these states over here have both the photons in them and the atomic states in them. And so these are manifolds separated by one quanta of energy. And of course it doesn't matter if it's the photon quanta or the omega AB, because you're supposed to be resonant, much more resonant than what this picture shows. So you're separated by whatever that frequency difference is. But if you look at these two levels, that would say in these two levels, it's n quanta of energy. This means during the whole resonant process, if there's no loss to the system, it's a closed system, you never go from here to here. You only stay here, all right? And so if this is the n photon quanta, it says that either you have n photons and the atom's in the A state, or the atom's in the B state, and to get there, you've lost one photon, so you have n minus 1 photons. And when you go back and forth, and this is what Rabi flipping is all about, is that you actually stay on one of these, and over time, it's either the A with the n photons, or it's B with the n minus 1 photons. And it just goes back and forth with the Rabi frequency, which is exactly this frequency separation. And it also says that you go between the A and the B state, with this frequency. You populate 100% here, and then 100% there, 100% here, 100% there. But you are staying here. The only way to go from this manifold down to here is to lose energy. You have to have n quantum energy and end up with n minus 1. This means that a photon has gone out, not in your beam, staying in your atomic thing in your beam, it's just gone somewhere else. And remember, I showed you the picture of my hollow fiber glowing. So indeed, photons are not staying in the beam, they're coming on out. Okay, so that is a loss. Now this picture actually came around when a scientist called Malo saw the Malo triplet. And so again, what's the Malo triplet? Is that he looked at the fluorescence for such a thing. So you would pump, and you would expect the fluorescence to also be the same, but no. When you pump, he actually saw from here to here would give you omega, from here to here would give you omega. But he saw fluorescence at omega minus this omega, from this level to this level, and he saw, sort of on the other side, from this level all the way down, omega plus omega. And so this is called the Malo triplet, and they use this idea to say, this is what's happening. So I look at that and I go, well, that's what we're happening, but we only have one side. I have to think about, why do we only have the red, we don't have the blue? But we'll keep going. So then, Boyd himself, while I was in Rochester, apparently, he and a grad student, fellow grad student while I was there, Don Harder, was working on this experiment. So they have this one strong beam, and they're not just looking for loss, they're going to have this other beam go through, and so you can actually pull a photon from this one. So you could actually start here and pull a photon and go up to here. Okay, and that's what they're looking at here. And so, and then they watch what happens as you tune through the resonance. And what happens is, on the red side, this is absorption, they get gain, and on the blue side, they get loss. Now remember, this is the picture I'm trying to look at. And on the blue side, we seem to go down into the continuum. On the red side, we seem to have this shoulder. So I'm going, well, that kind of looks like what we have. Okay? Question is, what is this? Because we're not putting in a second beam, but nevertheless, it sort of looks like what we have. So then, of course, I had to remind myself, what does one see in Raman? Because we're doing Raman, we're not doing one photon, we're doing two photon, our resonance. And so our resonance is because we have a pump and a Stokes driving this resonance. But we can also have the anti-Stokes and producing the pump. So linear Raman only has one input, not the two. So the input is this blue. And if you start at the ground, you would see the Stokes. And if you start here, this transition with this pump, you would actually, and you could see it go the other way around, I suppose, but you would see, if you start with the lowest level, you're going to have anti-Stokes absorbed, and the Stokes and the pump made. So those two pictures have me starting to think. So the other thing to take note, go to the two photon one, is that what is this Rabi frequency? There's two components to it. There is the Rabi frequency that comes about because of that coupling that you see between, in this case it would be the dipole moment and the electric field. And then there's also this detuning. Because this one was the only one, if you tune exactly on resonance, the Rabi frequency would be exactly that. But if you detune, then the total frequency is the sum of the squares. The square of the final one is the sum of the squares of these two. All right. So now let's look at the two photon, and they come from these block equations, which is where the one photon also comes from. And these ones also showed up in all of that theory I showed you. There's a few things to note. In the one photon case, it had to be real. There was no phase. But that's because there was just the one amplitude. But now we have the amplitude and a different amplitude star. And its shape can be different than the other shape, and so we can end up with this phase there. This intensity is this one. It's the omega j with the other omega j right back down again. So this is the intensity. And as I said, this one can cause these levels to shift. And so your detuning is not just the different, the omega 2 one, which is this, minus the omega s, okay? You actually have to change maybe this if this is showing up. With our laser, we set our central frequency, so this is 0. This one comes up because we're using two chirped pulses and changing in time. And so what we're doing is changing the instantaneous frequency, and this is what this term is, okay? Because d theta dt is omega. And so we probably have to redshift when we have intensity. So I'll come back to that. But you can see it's more complicated. So what do we think is happening? We think that that Stark shift causes a redshift, and we know in SF6 now that it does. So it causes a redshift, so we always have to be red detuned just to stay in resonance. If you're red detuned, then you're always in the lower of your tube. In your manifold, you always start in the lower level. If we're in the lower level, if the population is down here, then what this means is our omega j is strong. Again, we're still talking about linear scattering out of the beam going down the pipe. We're talking about sending it somewhere else. So, oh, my battery died. Well, alrighty. Yeah, oh, you have another one here.
Yeah. It's the red shift.
So we have this redshift here, yes. So we pump up, instead of coming down, back down, which will give you just the omega j minus 1, you can see we have gain on the redshift. We also then, if you have to start on the bottom, then you have the blue shifted 1 actually being absorbed to make the omega j. And so this is why we think we see the blue dip on the one side and the red shoulder on the other side. It sounds weird that it still works, we won't drive the laser. Anyway, it's one of those things for us physicists to ponder. All right, by now I have a new master student. He wanted to plot the data differently. And so this is the time delay between them. So this is when we would be right on resonance with the 23.25 terahertz. It's true, just like in the Harris case, that when we blue shift, we get less and less orders. But you'll see it also never leaves the Raman. It's just where the Raman should be. When we redshift, if it was 4-wave mixing, you would see that this would go with the delta omega that we're driving it at, if it's 4-wave mixing. And then each order would get more and more and more and more over like this, because the top here would be some minus delta omega between each one, so it would be quite large here, and this would be the blue one, and so it would get further and further apart. And that's not what we see. We see it actually jump to another level. Okay, and this is why we think it really is this 2-photon Rabi/star effect happening. Oops, wrong one.
You want us to change the...
No, it's all right. I can go double fisted. All right. So we made sure that it was a nonlinear effect, and so we changed the energy. And indeed, if the energy is low, we don't see these shoulders. When the energy goes up, we start to see the shoulders. We see them move over more. So it's a nonlinear effect. Here's the other one. We wanted to make sure it wasn't us doing something weird. So now we've actually changed the frequency away from the 23.25. So this is almost 1 full terahertz closer together. And you'll see that we actually had to change the timing to blue shift from that in order to be where you want to be. And when we actually went to 22.9, we were best right at 0. The other thing I want to point out, back to the beginning of my talk, is that you will see that what we have is really broad individual peaks and separated by this. So we should get very few, if we can compress all of these, we should get very few orders in our train. And we'll have our intense single femtosecond pulse. The only trick now, this is the last, it'll be the last slide I show you, is how easy is it to do that. All right. Oh. Okay, so that gets to how to measure this and the troubles that I'm having. Oh, the troubles. Okay, so we're doing second harmonic frog, frequency resolved optical gating. We're doing a cross one. So we take one of our pulses, because this is going to be a complicated, both the Raman and this redshifted shoulder together. We don't want to just interfere those two and try to look at it. We're going to take one pulse that we know, which is one of the pumps, and then we're going to correlate it with this whole thing, the whole spectrum. But because we're doing frequency resolved optical gating, the blue that comes out, we look at the spectrum. So we only look at the first anti-Stokes order. All right? And so now we're going to look at the frequency resolved optical gating of that, which says, oh, because we have autocorrelation in time, we're going to have the autocorrelation in time, not the pulse duration in time, but the autocorrelation of it, and then the spectrum in the other direction. And this is what we get. You'll see we have these two distinct lobes, at least for this version. Okay. This is what the frog gave us, and so it sort of matched. This I think is experimental due to some kind of weird diffraction. So it gave us this, but this did not give us any kind of sensible answer either. Like there was nothing that we could explain from any physics that we had. We then decided we would come up with our own two-pulse model, and we could actually get it fairly good. But what this two-pulse model, and actually what this frog showed, is that we had a red pulse. The red shoulder was out well ahead of the Raman. But the Raman is timed to the pump. So you're going, well, I don't think we can be driving something that happens before the pump even gets there, okay? And the dispersion was not near enough to get this red shifted shoulder, which is only a terahertz ahead, to be out ahead, without ahead by a picosecond. No, not possible. And finally it dawned on us that of course we don't really know the theory, and if you add two chirped pulses in phase, you get a chirped pulse that's halfway in between multiplied by cosine function. That's what you would get. This is the same thing as if you have just two pulses, two very narrow line pulses, you get a cosine function. Two broad pulses gives you the halfway in between with the cosine function. But if they're actually out of phase, and remember that these two things in the dress states, one is called the phase and one is called the antiphase. One is the A n photons plus B n minus 1 photons, and then the other is A n, did I say minus? Whichever, one's plus and one's minus, okay? So then I thought, okay, let's add them with a pi phase shift between them, because one's going between the same states and one's going between different states. And if we put a pi phase shift between, that gives you the sine function, not the cosine, and that says there's a 0 in the middle. Now you have a chirped pulse with a 0 in the middle, and you're chirping from red to blue. That would look like a red pulse followed by a blue pulse. And so this is what we think we have, is that these two pulses are there together in time, but they're out by pi phase shift, and that's what the last model is about, and so it also shows us. So this is our problem with using second harmonic frog, is that it does not, for very complicated things, give you unique solutions. And so we have to find a new way to measure this that would hopefully give us a unique solution. So keep that in your mind while you're thinking about this. Okay, so finally, last slide. Nope, almost last slide. All right, I'm just going to repeat this so you know what we're going to look at. Is that what we're trying to say is it from 2-photon Rabi, 2-photon Stark? If it is, then we're only going to have the shift. When you always show these pictures, this is the adiabatic regime. The E is there all the time. We're in the transient regime. Our E is not there all the time. This I is a pulse in time. This means that if we detune so that at the peak of the, remember this is 0, if we detune so that at the peak of the pulse we're 0, then where I is 0, this is actually shifted. So we're going to have this delta. Also, when we shift in time, we're taking the peaks in time away from each other, and so when you multiply them, you're actually lowering this Rabi frequency while you're doing that. This is why I think when we actually changed the central frequencies and ran with them timed up, we actually got the nicest spectrum, because you could have the most intensity and already detune the right amount. Okay, so here's the latest results that I've gotten since arriving in Armenia. For the experiment where the pulses are timed up, the best two-step model is that, of course, if they're timed up together and the I goes to 0, there should be no detuning, which we see no detuning. And when the pulses are timed up, we will get a pretty big dip because of the Rabi frequency and also because of the I. And so this is the model, and it gives us good result as the frog itself. If we detune, you'll see that away from I, this is detuned. Of course, there's no light there, so you're not really going to notice that. But anyway, and also because we're detuned, we actually don't have as big an electric dip, and that gave us the best model when we were up that. Also showed that we get a lot more in the red shifted shoulder, possibly because we are resonant with the Stark shifted level. So this is as far as we are, but we're thinking we're now finally getting very close to saying it is the 2-photon Rabi that's causing this red-shifted shoulder. It's because we need to be red-shifted to see it and be resonant, and so we always start in the ground level. Because if we start in the top level, you would actually see the blue shift, just like the model showed up. And so I think that's the end of my talk, since I just got that a few days ago. Oh, which way am I? This way. And so, we have torn down the Tri-Sapphire. It was a 20-some-year-old laser. It wasn't working anymore. So, and unfortunately, then COVID hits. And so we've been trying to switch to a fiber laser, and it's been a problem. But hopefully we're going to get back up. We're not going to use a hollow fiber anymore. I have a Kagame fiber, so we only need microjoules and not millijoules. Hopefully, if we can figure out exactly what the chirp is, and if we get up to the higher orders and there really is only the red-shifted shoulder left, can we, with a dazzler or something like a dazzler, for those of you who know what dazzler is, fix that chirp? But again, in yesterday's talk, I said when we had that S shape, we couldn't compress it. You needed a nice linear chirp to compress. So we're stuck now with a Gaussian-shaped chirp. And so it's sort of a linear plus Gaussian-shaped chirp is what we have that we're now going to have to correct if we want to make short pulses. Not sure that we can, but we still live in hope. We always live in hope. And so that's it. These are all the many students that helped me. These are the undergrad students that helped me. And of course, it was Leonard Losaf that even got me going down this track. Anyways, thank you very much for your attention.